Hey BC Cal students, this video covers implicit derivatives. So in class, we've already talked about implicit functions. They're functions that can't be easily separated into either y equals something or x equals something else. So in this video, we're only going to cover how we would find these derivatives. We will connect the concepts of the product rule, the quotient rule, and the chain rule in finding some of these derivatives. So I'm just working examples from the textbook. If you're working with me, this would be page 146 and 147. Unless otherwise stated, we're going to be finding derivatives, and let's get started. So first, let's talk about the steps for implicit differentiation. We would derive as we typically would. We add a dy over dx to any y term that we derive. Now that's going to be different than if a y term just exists in the problem. We're going to group our dy dx's on one side, and finally we're going to solve for dy dx, and we're going to bask in the glow of a correct derivative. So the first example that we have is we'll do number 2 from the textbook. So again, I am just working from page 146 to 147. And we're doing number 2. So number 2 is x squared, number 2 is x squared minus, I need more room, x squared minus y squared equals 25. So this is an equation that could be written in terms of either x or y because it's easy to solve for either one. But to illustrate the principle of implicit differentiation, we're going to start by first, we're going to treat x as the independent variable. So we need to drop a nice, big, juicy derivative operator in the front. So the derivative of x squared is 2x. The derivative of y squared is 2y, but going back to our thing, we add a dy over dx to any y term that we derive. So we're gonna have 2y dy over dx equals the derivative of 25, which is 0. So then we want to group our dy dx's on one side. So imagine we move the 2x to the right side, we would get negative 2y dy over dx equals negative 2x. And so to finally solve for dy over dx, we divide by negative 2y. So we get dy over dx is negative 2x divided by negative 2y, which is just x divided by y. So now we bask for a moment, and then we move on. So now we're going to do number 6, which is a more involved problem that requires that we do we'll see. No spoilers. So number 6 is x squared y plus y squared x equals negative 2. And as we did before, since we don't have something in terms of something else, we need to indicate that we're going to do a derivative. So we're going to do a d over dx. Again, put a nice, juicy derivative operator around the entire problem. And in doing so, for the first term, let's use some different colors. We'll write the derivative terms in different colors. So for the x squared y, it's x squared times y, so we need to do the product rule. So we're going to have x squared times the derivative of y, which is dy over dx, plus y times the derivative of x squared, which is 2x. So these two terms come from the x squared y. And then when we do the derivative of y squared x, we're going to have plus another, so y squared times the derivative of x, which is 1, plus x times the derivative of y squared, which is 2y dy over dx. So these two terms come from the x squared y term, and this would just equal the derivative of -2, which is 0. So we want to group the terms that have a dy over dx. That's going to be this term and that term, meaning we should just move the 2xy and the y squared to the right. In doing so, we get x squared dy over dx plus 2xy dy over dx equals, so remember we move the 2xy to the right, so we get negative 2xy, and we move y squared also to the right, so we get minus y squared. When we're looking at this, the common factor they have is a dy over dx, so we factor that out, we get dy over dx times x squared plus 2xy equals negative 2xy minus y squared. And our final step is always going to be to divide by the term with the dy over dx. So we get dy over dx is negative 2xy minus y squared, all divided by x squared plus 2xy. So again, we had to do the product rule twice to get this derivative, and we group our dy over dx's, factor it out, divide by the term with the dy over dx, and we get our final answer. Number 11. Give me a moment. So for number 11, we are working the sine of x plus 2 cosine 2y equals 1. And again, because we don't have this solved for either variable, we're going to drop a derivative operator in the front to indicate that we're doing a derivative. Oh, you can see any of that. Excuse me. So we had sine x plus 2 cosine 2y equals 1. We put a derivative operator in the front to indicate that x is the independent variable. The derivative of sine x is cosine x. And then the derivative of 2 cosine 2y is going to be negative 2 sine 2y. And we also have to multiply by the derivative of 2y, which is 2 dy over dx, and that would equal the derivative of 1, which is 0. So if we wanted to, let's do two things at once. We're going to move this all to the right, and we get cosine x equals negative 2 times 2 is 4, negative 4. So when we add it to the right side, we're going to have 4 sine 2y dy over dx. And we would divide by this part, the 4 sine 2y, so we get cosine x divided by 4 sine 2y equals dy over dx. So let's go back and explain for a moment. The derivative of sine is cosine. The derivative of cosine is negative sine, so we have the 2 in the front, so we keep it. And this part, the 2y, remember, we never change the angle. The chain rule says we multiply by the derivative of the angle. The derivative of 2y is 2 dy over dx. And so then we add this to the other side. We get 4 sine 2y dy over dx. And then finally, we divide by 4 sine 2y, and we get this as our derivative. Number 13 is, let's see, we have y equals the sine of the product xy. And we're going to include a derivative operator, which would give us dy over dx equals, the derivative of sine is cosine. And remember, we never change the angle for a trig function. We never change the angle. We get dy over dx equals cosine xy. And then we're going to multiply by the derivative of the angle, which would require we do the product rule. So we're going to have x times the derivative of y, which is x dy over dx, plus y times the derivative of x. And we have to group the dy over dx's. The easiest way to do this is going to be to distribute the cosine xy to both of those terms. So we get dy over dx equals x cosine xy dy over dx plus y times the cosine of xy. We subtract dy over dx. We're going to subtract this term to the left. So we get dy over dx minus x cosine xy dy over dx equals y cosine xy. And then we will factor out the common factor of dy over dx. So we have dy over dx times 1 minus x cosine xy equals y cosine xy. And finally, we divide by the 1 minus cosine xy. So we get dy over dx equals y cosine xy over 1 minus x cosine xy. Let's do example number 26. So for number 26, we're finding the derivative at a particular point. We're finding dy over dx at the point 2, 3. So the function is x cubed plus y cubed equals 6xy minus 1. I'll move this up and get some real estate. And we're finding, again, the derivative at this point. So when we do our derivative, we're going to include a derivative operator. So we get d over dx. And that would give us 3x squared plus 3y squared dy over dx equals product rule. So consider the 6x one term and the y a different term. So we would have 6x times the derivative of y, which is dy over dx, plus y times the derivative of 6x, which is 6, and the derivative of -1 is 0. So again, we group our dy over dx's, and that would give us, so let's do two things at once. This is going to move to this side, and the 3x squared is going to move over to that side. So we would get 3y squared dy over dx minus 6x dy over dx equals 6y minus 3x squared. We would then factor out a dy over dx, so we get dy over, you know what, actually, let's not do that. Anytime we have to evaluate the derivative at a point, it's easier to, once you have all of your derivative terms, even this step was actually unnecessary. We could substitute in 2 for x and 3 for y and simplify from there. We don't need the dy over dx isolated. So if we do that, since y is 3, 3 squared is 9 times 3 is 27, we get 27 dy over dx. And then since x is 2, that's going to be minus 6 times 2, which is 12. So minus 12 dy over dx equals, again, y is 3, so that's going to be 18 minus X is 2, so 2 squared is 4 times 3 is 12, so minus 12. And we get 15 dy over dx equals 18 minus 12 is 6. And finally, we divide by 15, so we get dy over dx is 6 over 15, or that's 2/5. So anytime you have a point, you can just substitute it in immediately when you have the derivative. It makes solving a problem much easier. We're going to move on to what I would say is going to be the final example in this video, and we're going to do two things at once. So for the final example, we have 1 minus xy equals x minus y, and we're going to find the value of the second derivative at the point 2, -1. So we're going to do the second derivative d2y over dx squared at the point 2, -1. And to do the second derivative, obviously we need the first derivative. So first we're going to just slap a derivative operator in the front, and that will give us the derivative of 1 and 0. So now the negative x is one term and y is another term. So we're going to have negative x times the derivative of y, which is dy over dx, equal, minus, well, we'll say like plus y times the derivative of negative x, which is -1, equals the derivative of x is 1, the derivative of y is 1 dy over dx. And assume we move the x over here and we move the 1 over here. So we would get -1 minus y equals, we're going to add the x dy over dx, so x dy over dx minus dy over dx. And we would factor out a dy over dx, so we get dy over dx times x minus 1, and finally we get -1 minus y over x minus 1 equals dy over dx. So we're going to continue this second derivative up here. Now what we do is, when you're doing the second derivative, you still apply a derivative operator, but you already have the dy over dx isolated. So when we do the derivative of the left side, we're going to have to do the quotient rule, which would give us, so we're going to have the low function x minus 1 times the derivative of the top, which is negative dy over dx, minus the high function, which is -1 minus y, times the derivative of the bottom, which is 1 all over the bottom function squared, x minus 1 squared, and that's going to be our d2y over dx squared. Oh, let's get some room. Just a moment, kids. All right, there we go. So in doing this, we'll zoom out just a bit. We can substitute in this for dy over dx. There are two ways to do this. We'll cover both. So one way we can do this is having x minus 1, and we'll put the negative in the front. So we'll take this negative and just move it out to the front. So we have x minus 1 times the quantity -1 minus y over x minus 1, since that's dy over dx, and just minus -1 minus y over x minus 1 squared. And since we're evaluating this at 2, -1, it's easy enough to substitute in 2 and -1 for x and y. And in doing so, we'll just put at 2, -1. So we would get a negative times, so since x is 2, 2 minus 1 is just going to be 1. And since y is negative 1, we're going to have negative 1 minus negative 1, which is 0. So 0 over 1 minus negative 1 minus negative 1 over 2 minus 1 squared, which would equal 0 because that's 0 and that term is 0. Sorry. So when we substitute in the point 2, negative 1, we get 0. So a quick recap is we did the second derivative by first finding the first derivative dy over dx, and to do the second derivative, we took the derivative of that quotient, which required that we do the quotient rule, and anywhere we had a dy over dx, we replaced with the expression for dy over dx just in terms of x and y. That's why this negative dy over dx turned into this expression for dy over dx that we have right here. So a quick recap again is to do implicit differentiation, these are the steps. We derive as we typically would, we add a dy over dx to any y term, we group the dy over dx's on one side, we factor it out, and then we solve for dy over dx. And lastly, we bask in the glow of a correct derivative. I hope this video was helpful. If you still have questions, please feel free to talk to me in class before school or after school. Thanks.